topic of my today's talk is the exceeding historical exposure. So we will focus on uncertainty of the data, not of the model, but of the data itself. And the main source of the uncertainty we are focusing on is the exposure. So let us start with the session-based recommendations. Recommendation systems are tools for information retrieval. So if we have a large e-commerce with a lot of products or a learning platform with a lot of courses to do, or perhaps some platform with news, there is a lot of content. And we are not able to interact with all of this. So to increase our satisfaction, to make our experience a lot better, there is a need to personalize this content, to select the items we are exposed to select the news we are served, to select the courses we are recommended to do. And it's beneficial both for the user, because we have a better experience and we are not influenced by a lot of content, unwanted content actually, and for the provider, because it increases our screening time, our engagement, the purchases, so it's beneficial for both sides to personalize the content. In the session-based recommendations, we consider anonymous user sessions. So if I went to an e-commerce and view my favorite books each day, those sessions are not linked to each other. So only my daily short session is one observation, one sequence of items. We will use the notation that I is the set of items, S is the set of sessions. Each session is just a sequence of items, so it's a quite short sequence. In the data we are working with, it was like 5, 10, 12 maybe items. And the task is to having the session prefix, provide recommendation, it's a list of items, for example, 20 items, so that the last item from the historical session, the target, is present into the recommendation. In session-based recommendations, we don't focus on users at all. So if you know the graph neural networks for the known user scenario, they are always bipartite graph with a part for users and a part for items. As a session, anonymous session from the history can never be continued, which is not the case for user who may come back. We consider the graphs only of items. So each sequence of items becomes a path in this in the item graph, and edge means a co-occurrence, so going from one item to the other. Here is the example architecture we are using in our experiments. It is the SRGNN model, a quite basic graph-based model for session-based recommendations. As I told it at the beginning, this approach is model agnostic, so we used this example to test the approach, to implement it and to have a point of focus. However, it can be easily translated to any model architecture. In this model, we have a gated graph neural network, which converts the graph of sessions into item embeddings. Those are these E's. They are just vectors in a high-dimensional space, exactly like for words in NLP. Then we have some attention layer, which provides us with some global embedding of the session and some local embedding of the session, which are actually, the local one is just the embedding of the last item. This is this arrow here. We have a linear transformation, and we obtain a session embedding, which can be seen as a prediction of user interest. And then, using the embeddings of the item and the prediction of user interest, we look for the items which fit the predicted interest best. It's done mostly with the dot products and the transformation with a softmax layer. In training, we just look, does the predicted score and do the predicted items match the historical target, which is one hot encoded and trained with the cross entropy loss. Okay, so let us move to the challenges related to uncertainty of the data. Those are the challenges we are addressing it with our approach. However, there are much more challenges in the recommender systems. And what I should mention also is that we focus on a strictly collaborative scenarios. So we do not have any information about the data. I know it's the product 1, 2, 3, 4. I have no idea, is it a shirt, is it a book, what color is it, what brand is it? Absolutely no information. Similar items means that they occur in similar context. So the challenges we face are first, implicit feedback. We cannot ask a user after each click, do you like the product? We assume that if he clicked or she clicked, it was the product the user liked, which is a quite bold assumption, especially when we have such cheap actions as clicks. We can go see the item, say oh, no, 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 and go back. However, the information how do we find the item is not present in the data. So it's the first source of uncertainty. The feedback is not something we can strictly rely on. The second thing is the exposure bias. And this is the thing we are focusing on in our approach. Exposure bias is that we select, so we click, we buy items we are aware of. We click items that we can see. So for example, if we go to some social media platform, the posts we like are those which we have seen. We do not select the items we like from all available ones. So it's a huge problem in recommender systems. And this exposure bias is also related to popularity bias, but because in most situations we are served with most popular items, and they dominate the data absolutely. And the last thing, also related to those two, is data sparsity. So each session, if it consists of 10 clicks and we have like 50,000 of items, the data is extremely sparse. And if we don't look at the session, the sparsity of the session, but the sparsity of the item, the rare items are extremely sparse. So we have very few interactions for them, which complicates modeling them even more. So those are like theoretical symptoms from the data, and how do they influence the model itself? Because as you know, garbage in, garbage out. So if the bias is present in the data, it perhaps is present in the model and in the model predictions, so the recommendations in this setting. And the symptom of the bias are easiest to measure with popularity, because this is something we can measure in the data, and this is why we focus on the popularity in the symptoms. So at the upper picture, you can see Disney projections of embeddings. So those are the vectors representing each item. Left and middle are the points. The right is the density of the points. So we can see that there is a huge concentration in the middle of the picture. And if we look at those two pictures, the blue ones are the rare items. The yellow ones are the popular items. So we can see that the rare items are cramped to each other. So we cannot easily distinguish between the rare items. And it is visible at the Disney projections. We also took a look at the original embeddings, calculating the cosine distance to the closest items, and it confirmed that we have some very cramped items, which cosine similarity is almost 1, so they are very close to each other, and the closest are the rare items, for which we have only a few of occurrences. So how to deal with it? We proposed an approach which consists of 3 modules. The first part is focused on embeddings. So we want to prevent encoding the popularity, which is related to sparsity and exposure in the embeddings. So we add some normalization after the gated graph neural network, and some regularization for embedding uniformity. So we want to prevent this cramping, but adding a penalty term for uniform distribution on this hypersphere of latent space of being a hypersphere for embeddings. The second part of our approach, so the second step, is to add some randomization into the session prefix. So we augmented the data to express the user interest in a dense manner. And the third component is augmenting the targets. So we added some noise also into the targets. Okay, so why do we normalize the embeddings? It's also known from the literature that popularity is very often encoded in the embedding norm. And if we provide the scores of each item using the dot product, the norm influences the score quite strongly. So a product with a long embedding is recommended more often. So it's the reason why we want to normalize it. And below you can find the radial basis function, also called the Gaussian potential, to regularize the embeddings for the uniformity. It's minimalized for the uniform distribution, so it forces the model to provide uniformly distributed embeddings. It's a technique also known from representation learning, from self-supervised learning, from some unsupervised approaches. The second module was focused on uncertain user interest expressed in the session prefixes. So we assume if the user clicked some green shirt, it's not that the user dreamed of that particular shirt, but something similar to what he has clicked, in fact. So we want to put some randomization and to treat the user interest as some random variable. So we assumed that the session is not a direct expression of user interest, but it's a realization of a stochastic process. So those x's here are the random variables describing user interest. The session, so the items we have in the data, are just some realization of this process, and we want to retrieve the true user interest from the data. As we have only one observation for the current user interest, we assume that it is a random variable concentrated around this item with some fixed concentration parameters. So we fix the spread by some hyperparameter tuning. We assume that the distribution of the random variables is the von Mises-Fischer distribution, which is quite strongly related with Gaussian distributions. So it can be seen as the Gaussian for the spheres as we work with spherical embeddings. So it's the normal distribution conditioned by working on a sphere. And as you can see here in the formula, it's also quite similar to the softmax function, which was used to produce the score for the embeddings. So it is quite naturally related to the architecture of using dot products and the softmax layer for spherical embeddings. And the third component is focused on the target uncertainty. So we assume that if the user were aware of some other items, he may have made some different decisions. So the X here is the true user interest. As you see, it's also marked with, it's also somehow blurred because we are not sure, and the user may also not be sure what he really wanted. He selected or she selected something most similar from items which the user was exposed to. So the most similar item from the banner here were those trousers. However, if there were space to provide more items and to present more items to the user, the decision could have been made differently. So we may select something more similar to what we really wanted. So to simulate the situation and to simulate this exposure, we split the probability of the target for the true target and for a number of fake targets to simulate the extended exposure. As you can see, the stochastic modules incorporated into the neural network-based model are just putting a lot of noise into the data. And what is quite surprising, it helped with the results. So shifting the distribution here, so you can see that all the distribution is shifted somehow to left. So the items we prevent from cramping the rare items, which is quite obvious as we regularized the model for it. However, computational experiments on the DGenetica and the UChoose dataset and some modifications of the UChoose dataset which simulate different levels of popularity, because it's the main difference between these two datasets, showed that first, for the DGenetica, which is less biased with popularity, we managed to increase the accuracy of the recommendations, which is quite surprising. So adding this noise to the data, both to the prefixes and the targets, and having this regularization for better embedding quality, allowed us for better generalization of the model. So it was quite surprising for me. But this is how the model works with less biased data. For the UChoose dataset, which is quite highly biased with popularity, we stayed with some similar level of accuracy measured with the hit rate is actually here. So NISR, which is the best model here, is an extension of SRGNN, has 71% of hit rate. Original SRGNN was 70%. We are like 70.8, so it's almost the same result as the original model. However, we managed to decrease the average recommendation popularity. So the items which we recommend to the users are less popular, and for both datasets, the coverage improved. So it's also a good sign for the quality of our recommendations. So to conclude, recommendation systems are a crucial business tool and a vivid field of research. Incorporating stochastic models into the models allow us to directly address the uncertainty of the data. Recommender systems have some specific challenges, like the popularity and exposure biases. And using these hybrids of deep and stochastic models allowed us for better model generalization. And all the noising, which I have provided here, is done in the latent space. So we can work on some mathematical representations of the items without touching the data directly. Okay. So thank you very much, and I'm open for your questions.